this computer, and I think I'm recording already.
It is recording, yeah.
Okay. Okay, so just 1 second. We have more people joining. Okay, so I will, yes. So I will share my screen. So I think you're seeing it now. Yeah, sorry. I think I have to go here and admit. Okay. Yeah. And then I have to close this. Okay. So I think I'm ready. Sorry for the. Okay. So first of all, I think I would like to start saying thank you. Thank you very much. When I sent out the invitation, I thought that maybe some people would like to learn a bit about the code, but we are, I think, 50 or even more than 50. So it's really encouraging, and I think I'm really happy just for that fact. So thank you very much. And then I think we can start. I will try today to give an idea of what I think we can do in this course. And the idea is that it's everything, for, at least my impression is that is open, so we can adapt to things that you may consider that are more important, that some things that I believe we can start with. And also I think that I would like to take this as a long-term course. I think some people are maybe busier now, or they want to go sometimes faster. But I think we can think about this course as something that we are doing constantly, and we can have different content based on your interests. Sometimes we can focus on some things, and then we can focus on other things, and then you can join or not, depending on your priorities. But the idea is that at least let's try to have some idea of what I want to do, and then let's discuss it at the end. So for this reason, I put the title an online course about desire and much more things, because I think we can cover a lot of things. And then just let's start with with some things. So first of all, I sent a reminder yesterday, and I think I put everyone that I had on the list of participants. But if you didn't receive that mail, then just let me know, and then I will add you to the list of participants. And also the people that were contacting me this morning, I already added you. So I think at least I covered the new members that they contacted me this morning. But if you didn't receive anything yesterday, then just let me know, so I will add you to the list. Then I think for me, I think I'm able any Thursday or Friday. So I think the best thing is to create a doodle poll. I will do it probably today or tomorrow morning to decide which day you prefer, and we can set it as a weekly meeting. And also I will propose some reference times. I think we can move, for me, between 2 p.m. and 4 p.m. I think it will be okay. So maybe for the US side is going to be more convenient. So I will prepare that. I will send it to everyone, and then we can decide which days we meet. So then I think we already discussed that, but just to let you know, I think it's really good to record the meetings. And if something that you see in the meeting is not, so you don't like how we appear there, or if you make a question and you don't want to appear, we can edit that later. But I think it's fine. It's like a conference. Sometimes you said something and you said, oh, why did I say that? But it's fine, and no one is going to judge you. Okay, so then I think this is what I was saying at the beginning. I see this as a flexible course. Okay, so we can decide what we are going to do next week. So then if you see that it's not so interesting for you, you can say, okay, I'm not going to come, but then you can come later when we are doing other things, because the idea is that we want to make it helpful. We don't want to make it restrictive or something really not open. And also, as I said, please invite anyone that you believe would be interested in attending, because I think the more people we are, the better. So we don't have any problem of having more people. Okay, and then I really would like to show you a lot of things. I said design, and I think we will focus on that. But I think it's an opportunity to also teach you a lot of things that are related somehow with the things we want to do with design or with other codes. So I think I will try to teach you more things. And also I would like to ask maybe Basilio or Han also to teach you things that are not strictly design, but I think it will be beneficial for you. So in that sense, at least in my case, I will share with you my programs. I don't have any problem with that, but I just want to tell you that they are basically functional. So don't expect to elaborated programs, and they just work. So I don't judge me in that sense. And also for that reason, just don't hesitate to change them. And as soon as you understand what I'm doing, just go ahead. They are usually in IDL, so if you prefer to just transform them to Python or the language that you use, it's also fine. I think the important thing here is that you start using the tools, you understand what we are trying to do with the tools, and then you adapt them to your style. And in fact, I think also improvements are more than welcome. So if you see that I'm doing something and it can be done in a different way and in a better way, just let me know, because I think I also can learn a lot from you. Okay, so then let's start with a general idea of what I think we can do in this course. So first is learn how to use Desire. Desire is the name is departure coefficients Stokes inversion based on response functions. You can see it in the paper. Today I will explain some things, but I will not enter in too much detail. I think I prefer today to just give you an idea of what I think I would like to do. So then we will learn how to do synthesis. We will learn how to compute response functions. Later on, we will discuss what are response functions and why we believe that they are very important. And we will also do inversions. But at the same time, I think I would like to teach you also how to work with 3D MSD simulations. And this is not strictly design only. This can be done with SER, this can be done with RH, with any code. So the idea is that I will show you how I transform Bifrost simulations, Muran simulations, Mancha simulations to work with the codes that we're going to cover here, in particular design, but also SER or RH. And as I said, I would like to share all the things that I've been working in the last years. And in particular, it will be, for example, comparing simulations and observations. So as soon as you have the simulations in the proper format, it's almost straightforward to compare them with observations. Then I will also try to teach you how to compute Stokes profiles from those simulations. So then you can examine the spectral signatures of, for example, any physical event that you have in this simulation that is of interest. You can check what are the spectral signature of those events. But also to study the possibility of observing those effects with a given instrument. So if you're interested on something that has a polarization signal of, I don't know, 1 × 10⁻⁵, then you can check if with a given noise and a given instrument, you will be able to see them or not. So there are, I think, different topics, but it's something that I've been doing in the last year. So I would like to teach you how to do all those things. And the idea is that everything that you see there is helpful for, on the one side, for improving simulation. So sometimes simulations, they look more or less okay, but when you synthesize the spectra, you see that there are some difference comparing to observations, and sometimes there are some room for improvement. So if you interact with the people doing the simulations, I think it will be helpful for them for improving the simulations. Also for improving how we perform observations. So based on the requirements for observing a given physical event or even solar feature, based on that you can prepare better observing proposals and be more competitive when there are calls for them. Also, for improving how we analyze those observations. So then if you know how to embed the Stokes profiles, you will extract a lot of information from them. So learning all these tools, it will be helpful in that sense. And at the same time, if you have the possibility of taking a simulation, produce Stokes profiles, and then degrade them with characteristics of the instrument that you are trying to reproduce, then you can really tell the instrument designers if the design is working, or maybe there are some things that you could change for improving its capabilities for that specific feature. Okay, so let me see. Okay, yeah, so let's go back. So the idea that I will talk a lot, I realized that having 1 week for preparing a presentation, it allows you to put a lot of content. So this morning I realized that I would talk too much and maybe this could be a bit boring. So I'm going to insert in the presentation some things, I would say cool things that I believe we will do through this course. And this will probably reduce a bit the difficulty of following the presentation. So in one case, I will show you how to take one snapshot from Muram. This is from REMPEL 2012. And just take it, transform it to a proper format, and then run a synthesis. And in this case, computing the continuum at 500 nanometers. So then you can reproduce some kind of observation. The idea is that for doing that, the details will come later, but I just wanted to show you that for doing this, I use SER for the transformation and also for the synthesis. And also not only continuum, but you can do the same for the full field of view. For example, the 6302 line. That is one of the most representative lines. So we had it in ODSP, and we have it also in DKIS. It's one of the lines that are going to be observed in this first call for proposals. So you can do these things. You can start from a sunspot, and then you can transform it in the proper format, and then you can do synthesis of the lines that you are interested on. And this case is only SER. We will do similar things with design, but I just wanted to say that we could use SER for that as well. Maybe I forgot to say, I think this is going to be a not very long presentation, but I usually talk too much. All the people that know me know that. So I think if you want to make a question, just raise your hand, and I think you can ask me. And if not, we can leave it to the end. But I think if you just have any question that appears comes to your mind at any moment, just raise your hand. Okay. So then, okay. So just let me go. How can we do that? Sorry, is that the video is blocking my title. Okay. So the online course. I think I hope to go step by step. I think we can work on this every week. Sometimes we could go faster, sometimes we would need more time. But the idea is that step by step, I think once per week, I can continue this for a long time. We will record meetings, so if you cannot attend, or if you attend and during the meeting something is not so clear, then you can watch the recording again and maybe it will be helpful. Or if not, you just contact us. Then I think as we progress, maybe it would be interesting to write guidelines based on what we cover. I'm not sure about that. I think it's probably good, but I don't know how will we do it. So if you have any ideas, just let me know. As we continue on this, just let me know any idea that you can have, and we can try it. I think this is very important, patience, mainly in inversions code. So what I mean is that first, design itself, it's new. So we know that some problems will appear, but the idea is that the more people we are, the faster we will find those bugs. So it will be easier for finding them and correct them. But also, and I think this is the main limitation, is that most of us, when we started with design, we still worked on other projects, but we had more time. but these days, most of us are really, really, really busy. So I think I can keep once per week meetings and preparing things, but I just want to warn you that if you send me an email, sometimes it will take more than one day probably to answer. So just be patient. At least we will meet every week. Okay. And also, I just trying to give you hope is that last year and this one, you know that this has been a complicated year, but I think we have learned to endure. So let's work together and try to learn a lot and go step by step. I think we have the time. Mainly, I see that there are a lot of young people in this meeting. So I think just go step by step and don't try to rush it. Okay, and then I think this is the key of inversion code. So it's a trial and error. So what I mean is that not only inversions, but also in synthesis. So sometimes you get a new snapshot. It looks very nice, a simulation snapshot, and you do the synthesis and some things are wrong. Intensities could be negative or could be zero, or polarization signals could be 100%. So if that happens, that is normal, then you may need to check again with simulation developers, and maybe there's something that can be done. So don't feel bad if you need to repeat things, even in forward modeling. So the same with observation. So sometimes you are trying to embed some data and something doesn't seem to work. And sometimes you believe that is the code, but sometimes it could be that the calibration is not or accurate, or it has some error or some incompatibility. So it's okay if you need to also go back to the person that provided the data, or you have to recheck how you did the calibration, because sometimes the code it's working, but is trying to fit something that is not compatible with the physics we know of the sun. So that's also okay. It's not a problem, and it's something that everyone does when they try to do inversions. And then inversion itself, you have to repeat. It's you cannot, well, you can try, but usually you cannot run once and then say, okay, I'm done, I'm going to write the paper after that. No, it's usually, it requires some trial and error. You have to sometimes tune some minor things that it doesn't mean that the first time the results are wrong, but they can be improved. So you will learn that there's some ways to just try, or some things that you can always try. So the intuition will come as you learn how to do inversions. But still, even in my case, I never expect to have a final result from the first inversion. I think this is something that is, I think it's inside the process of doing inversions. Okay, so then let's get in a bit on desire. Let's start with the members. So first one is David. I don't know if he's here at the end, but he will come at some point. So you see it here, I see it there. He's a very nice person, and he's an expert on many things. He's an expert in inversion, but also in instrumentation and a lot of things. And he has been one of the main pillars of desire. Then we have also Basilio. I'm not going to lie. This picture is from 2008. He doesn't look like that today, so don't be fooled. But it's difficult to find a picture of him, so I'm just speaking that. Basilio is great as well. He's an expert on inversions. He was the creator of one of the co-creators of SER in the early 90s. And he's the one responsible of coding everything. So he has merged SER and RH, as you will see in later, and he's the one that really coded desire. Then you have Han, that he's here today. He's also great. I think he knows a lot, and I just wanted to say that maybe probably radiative transfer, partial distribution are one of his key capabilities, but he's also really capable of also observation and instrumentation. So he's also great. And then he's the responsible of creating RH in the early 2000s. That is also the pillar of desire. So SER and RH are the basis of the code. Then we have Ricardo. He's younger, and he looks like this picture, but that's he's not lying, like Basilio. And Ricardo is also a key person, because I started working with him for making a parallel version of SER. But on the way, he has been the one that also making a parallel version of RH, and also making the parallel version of design. And this is really critical, because nowadays we will have a lot of data, and we cannot assume that we are going to embed just a few pixels. We are going to embed large maps, and this has to be done in parallel. And this is thanks to Ricardo. Okay, and then Esperanza. So if it's difficult to find a modern picture of Basilio, it's impossible to find any picture of Esperanza. So I just put her name there, and just you will meet her at some time, I hope. And she's an expert programmer, and I can just say that she's basically removing all the bugs that Basilio includes in the code. She's cleaning the code and making sure that it works as intended. So you have a functional version of Desire, mainly because of Esperanza. Okay, and then I'm just in the middle. So I'm just trying to make it work. And the idea is that I since the beginning, I was the one that was able to run RH, run SER, and also I was working with a parallel version of Ricardo. So I was the person that was able to interact with everyone, because I had knowledge of all the parts that we were trying to merge. So for this reason, all these arrows connect to me, and yes, you can see me as the person that is trying to keep things working together. Okay, so how it works. Just let me give you some brief detail. It's based on SER. As I said, it was created with Basilio, by Basilio and Jose Carlos in 1992. And it works more or less like it. So what I mean is that, for example, for running an inversion, that is the ultimate goal that we have here, the codes will start from an initial atmosphere, and it will try to fit an observation that you have. It will perturb the atmosphere in a given locations that we call nodes, and it will try to get to an atmosphere that produces a profile that is similar to the one you observe. Those perturbations are determined based on response functions. This is something that we will enter later, but the idea is that it will give you an idea of where you need to change the atmosphere and in which direction, if you need to increase the magnetic field, if you need to reduce the magnetic field, and then so doing that to get closer to the profile you observe. So this is basically what design is going to do. So for those of you that already know about SER, you will see that eventually it's not going to be too much different. In fact, most of the configuration files are the same. And for those of you that are new and you don't know anything about SER, don't worry, it's going to be a bit easy, or relatively easy. Okay, so, but we added new elements compared to SER, and I will summarize them here. First is that now we are taking into account non-local thermodynamic equilibrium effects, so non-LTE effects. And we do that through departure coefficients. And they are the ratio between local thermodynamic equilibrium populations, that are the ones that SER always use, and the non-LTE ones. How we get the non-LTE ones? So we interact with RH. So we run RH for computing the non-LTE populations of the levels that involve the transition of interest, or they produce the transition of interest. And from there, we can compute the ratio between those non-LTE populations and the LTE ones. And we will have the departure coefficients that will be our non-LTE correction during the inversion. And then we can do that in a single thread, in parallel, and also on a server or on a cluster. Okay, so at that point, just let me mention that it's okay if you didn't understand anything I said in this slide, okay? The idea is that I just put this summary here, and my impression is that I would like to come to the same slide in a few weeks, 2-3 weeks, and then go through it again with you, and you will see that at that point, hopefully, you will understand what I said here. So this is just an idea of what the code is. Okay, so another break. What other things I would like to do with you here? Okay, we have the same sunspot as before, but this time what I did is I took the the original simulation and I project it to 4 different heliocentric angles. This is mu equal 1, this is mu equal 0.75, 0.5, and 0.25. I did that with an ideal procedure that I will share with you. Then I repeat the steps from before. So then for each snapshot, I transform to optical depth, and then I run SER. And I computed a continued at 500 nanometers. So you can see how a sunspot will look if you have different projection angles. So again, this is not strictly design, but this is something that I want to teach you. If you agree, if you're interested in doing these things, that I hope so, this is something that we will cover during the course, because you can use it with design, but you can use it with other things like SER or RH or any code, or just because you want to study how the physical parameters will change. So this is also something that I would like to do during this course. And I hope you would like to learn how to do it. Okay, after this break, let's go to ingredients that we will need to run SER. And the idea is that I don't want you to memorize this, it's just that the next slide will be some kind of warning that some of the ingredients that we need, we don't have absolute control of them. So just let me mention what we need, and then let me explain what I mean about by absolute control. So for running SER in non-LTE, it could be synthesis or inversion, we need an input atmosphere. That's fine, we have that. Then you need to observe profiles, and those profiles, they need to be normalized to the local continuum, and also they need to be in a uniform spectral sampling. I will explain you how to do that when you don't have it, but I just want to highlight that this is something that we need to run the code, and sometimes you don't have it when you have some observations. But we have methods to solve that limitation, not limitation, the difference. Then abundances, you need them, and we usually use Asplon, and you will have them in the library of the code. And you also need a list with the spectral lines of interest, and in that list needs to include atomic information about those lines, wavelength, log GF, leveling, energy of the levels. And this is usually okay. So we have a long list that you can use. And then you use an atom. You need an atom model. So if you want to perform a non-LT computation of a given transition, so for example, calcium 28542, so then you need a model that contains the levels that will produce a transition. So then you can compute the populations of those levels. Okay. So, and then you need configuration files. We will go through this, don't worry. But then the idea is that what I wanted to say here is there are some things that we cannot control. And I think the most important one is the atom model. So we have several atoms, and basically for the most common transitions, we have already atoms that can generate those transitions. But in general, it's not easy to have atoms for any transition that you want to treat in non-LTE. So then if you want something different, it's fine, it's okay. The only problem is that in general, we cannot do it, or we don't have the time to do it. So sometimes we may need to contact someone that is an expert on making atoms. And then if that person agrees, then you can have an atom for that transition. But the baseline is that most of the lines, you may not be able to treat them in non-LTE because we don't have the atom that we need. Then I think calibrations of any observation should be carefully revised. And as I said before, if the normalization is not okay, if there's a straight line that maybe is not properly corrected or something like that, the code will work. The code will give you some results, but maybe they are probably not physical or not correct. So then we cannot really do too much about that. We can tell you maybe there's something in the calibration, and then you need to recheck, or you need to ask someone. but the idea is that we cannot really tell you if everything is okay or not, and then maybe the results are wrong, but it's not really the fault, the error of the code. It's just that maybe there's something in the data. But the idea is that before getting on that, we will work a lot with synthetic data. So you will see where the code is, or how much you can ask the code. And after that, if using the same configuration with a similar data from an observation, things are completely wrong or completely different, then you may start thinking that it could be the data itself. So the idea is that to learn and to try to find a configuration that you can use both in synthetic data and observations, try it on synthetic data, and then move from there to observation. And if everything is okay, it should work. Okay, abundances. I mentioned before that we were using those from us from 2009. The idea, I think, is our baseline, but we are not really forcing anyone to use them. So if you feel or you have already worked on that and you said, I prefer to use different values for given elements, that's fine. We are just having a file where we have the numbers and you can change them. I can show you how. Okay, atomic parameters. And I think this is also a big thing, because usually for the most observed lines, you have lab values, and also you have that someone somehow has characterized them. So then you can trust the atomic parameters for the most common lines. But for new ones, or for basically for new ones, I will show you how I do it. I usually try to use NIST, where you have usually reliable values, but sometimes they are not there. So you have to go to different bases, and there's maybe some uncertainty. So we should be careful with that. And there are some ways for testing that it looks okay, the values that you're giving, but there still is something that it's not related with the code itself. It's something that it comes from atomic databases. So we should be careful about that. So adding lines is possible, but I recommend always do it carefully and slowly. So just checking that everything looks consistent. The same with broadening effects due to collision with hydrogen. So you have a bit more information in the paper, in the draft I send you. And the idea is that we use them to better fit the observations. And in principle, for most of the common transitions, I already have the values, I already computed them. But every time that you need a new transition, either LT line or non-LT line, they should be computed. And the idea is that it's not difficult. It's delicate because you have to know how to do it. And in my case, every time I do it, I still ask Paul Barclay, just to double check that it looks reasonable. And I think it will be fine to ask him, maybe not 200 mails, but I think I can revise it. And if there's some doubt in a given transition, then we can double check with him. But the idea is that if you add a new transition, you have to add this process of computing the broadening parameters to really use the best we can do for fitting an observation. And then I think here is just that I will try to provide you guidelines. And the truth is that if you look at how Basilio and me do the inversions, we do it in a very, very different way. So the idea is that I will give you probably both ways, although I don't agree with Basilio. But the idea is that you should be the ones after that trying new things and checking if something that you feel it could improve the inversion, you just try it and you can probably make it work. So this is what I call the magic of the inversion, because you will develop some intuition, and sometimes the general configuration will work, but maybe you think that some change, it could be on the weight you give to a given parameter, on the number of nodes that you use for fitting the atmosphere. This could really help the inversion. So the general configuration will work, but feel free to try things. Don't feel that the code will stop if you try other things. It will work, but most of the time probably will work worse, but maybe it can improve. So don't be scared to try things. Okay, so where we are. Okay, I think this is more or less the general idea I want to have for the course. Okay, so install the code for single thread computations. So we will take 1 pixel, 1 atmosphere, and we will run synthesis, and we will try for that process to understand everything that we are doing. Or if we are using lines, if we are using a given spectral sampling, if we are using a given atmosphere, everything. So after that, I think this can be exchanged, but probably I would prefer to start with response functions because it's a forward modeling process. And the idea is that I would like to teach you how to compute a response function for a given set of spectral lines and for a given set of atmospheric parameters. And then I will try to explain you what you are obtaining from there. So what is a response function and how you can use it for a lot of things. Then for the same pixel that we have synthesized, then we can run the inversion and we will check how it works. We can even modify it a bit, the pixel itself, for example, adding noise or adding other things. So just to check how we can invert the profile. And then I would say that we can also invert one spectral line from, for example, from the atlas. That is something that you have a very good spectral sampling and we assume that they are well calibrated. So we can try also that. In the previous case, in the third one, you know which atmosphere you need to obtain. In this case, you don't know it, but as it is the atlas, you assume more or less how it should be. So still in those cases, it's more or less like a control environment. So you know more or less what you need to obtain or more or less what it should be the result. So it's like a first safe test. Then I would say that I would recommend to move to installing the code for the parallel computation. And the idea is that they are different. So you have the main code, the desired code, and then a parallel wrap that is going to call the code, distribute it for different cores, and then run it. So I think it's okay if we do it in a separate way. So first we learn how to use desired, and then we start with the parallel code. And there, I think we can just go to the example that we did in the paper. So we run the synthesis for a bifrost snapshot. We can compute the response functions using desired. And also we can run the inversion of a region of interest. So here it's not only 1 pixel, it's several pixels, but still you can see that in general, we are still in this safe environment that I was trying to mention, because you know exactly what atmosphere you need to obtain. So then you can try several things, and if you get closer to the solution, it's good. If you get farther, then it's bad. But still, you can know more or less how you should move, and then from there you can have a general configuration that then you can use on observation. Okay, and the idea is that I would say that at least we have 2 types of observations. That they are a spectrograph where you have very good spectral coverage and usually uniform. So it's, I would say from the point of view of preparing the code is easier, but in general, it will work for both cases. And then you have filter graph that the good thing is that you have a 2D field of view that's very good, but usually you don't have a lot of spectral points, and sometimes, or most of the times, they are not uniformly distributed. So there's a middle step that we need to take for adapting those profiles to work with desire. But we have been working on this, so it's not a problem. It's just that it's an extra step that you don't need to take with the spectrograph observations. Okay, another break. This is the step 2 that I was saying before. So we have a bifrost snapshot. It was already computed, so transformed to optical depth. And then from there, we ran a synthesis. In this case, it was multiple atoms. It was sodium, potassium, calcium, magnesium, just to check that the code behaved well with multiple non-LT atoms. And then we did the inversion of those profiles. So this is the original atmosphere that we use for the synthesis. This is temperature, velocity, line of sight magnetic field. This is height, optical depth, so lower layers and higher layers. And then this is atmosphere we obtain inverting the profiles, but starting with an atmosphere that everything was constant here with height, and also here was constant. And it was much smoother in temperature. So the code was able to introduce gradients, and you can see that, for example, this red, white, blue is here. Then you see this thread that is going in this direction. So it means that it's moving to different pixels is also present here. So in general, we believe that the code is working well. Of course, we have nodes, so then we don't have a smooth shape that we have here. But in general, I would say that we believe that the code is working as intended. So this is what we try to do. And you can play with different configurations to see if you improve this. That is also good. So as before, I just want to say how I did this. So the transformation of the initial Bifrost, the original Bifrost atmosphere to optical depth, to the one that we need, was done with RH. And then the synthesis and the inversion was done with design. So as you can see, before I was using SER, and now I'm using RH and then combining it with design. Okay. So then I think this is the key of today's talk. So I think for this course we have mainly two options. So one is to directly go to two slides before, so synthesis, parallel, and then observations. So to try to go through all these points using design, or to learn first how to use SER and RH, covering point 1 and 2. So I mean synthesis, response functions, inversion of a single pixel, then synthesis, response function, and inversion of multiple pixels with SER, and also synthesis in parallel with RH. So we can do those two things. So in my case, I think option 2 is better. And the idea is, I think it's better because first we will learn how to use those codes that, as I showed you before, I use it daily. So I still, if I need to transform an LTE simulation, sorry, a photospheric simulation that it works with LTE lines, I use SER. I don't use Desire. So for example, for Muram or Marcha, I use SER. If I'm going to compute LTE response functions or inverting LTE lines, I still use SER. In the case of RH, I still also use it if I'm only interested in synthetic spectra. I need it for transforming the Bifrost snapshots. You will see why I need it. But still, if I need to transform a simulation that covers photosphere and chromosphere, I think, at least from my point of view, the best way of doing it is through RH. So I will explain you how, but for me, I'm not going to stop using RH even if I can use Desire. And also for computing non-LTE response functions. So I mean numerical non-LTE response functions, I think it's really easy to do it with RH, and it's what I did in my previous works. And also I think one of the key elements of learning first SER and RH is that you will learn the basis of design. And it will mean that you will understand why we are putting some configuration in the RH configuration files, or why we are putting some configuration in the SER part of design. So I think it will allow you to know why you are putting some things on the configuration files of design. So it will be, I hope, less black box, but sometimes it's a problem, and you will understand more what you are doing. And also, as I mentioned before, we have a lot of young people in the audience. So I think they are new to solar physics. And also we have people that they are new to inversion codes. So I feel that learning first SER and a bit of RH, it will be a good warm-up. Because as I said, when you know how to use both profiles, Desire and SER, you will see that they are sharing a lot of similarities, and also RH. So I think you are not going to lose your time if we go for option 2. So as I see it, yes, sorry. And as I said before, I think After learning SER and RH, you will go back to slide 5 and 6 and you will say, okay, now I understand everything that is said there, hopefully. Okay, so then my proposal is, just given rough numbers, we could start, if you agree, then we can discuss it, but we can start with a very brief session about SER, synthesis, inversion, transforming simulations, as I show you, for line of sight computations or projecting them, and computing analytical response functions. You have to realize that all the configuration files, or most of them that you use for SER, are the same that you use for Desire. So if you learn how to write the spectral line information in terms of wavelength, atomic parameters, and everything for the line list file, is the same for Desire. So everything you learn here, you will just translate it to later in Desire. Then another session for running SER in parallel that I think it's good, because if some of you is interested in inverting, I don't know, Hinode-SP or doing tests for HMI, I think it's better if you use just SER. You don't need to make things a bit complicated with Desire, because it requires more interaction and more things. So for those studies, I would say that I would use still SER. And then I would set one session about RH. We can do very, very simple tests about synthesis or transforming simulations. That is, I do it as a synthesis. And then if you are interested, we can also compute numerical response functions. And you can have some knowledge that I think is going to be useful for later. And at the same time, then we can decide, but I guess that as you are already going to get familiar with SER in parallel, you will see that the Python wrap is very similar. So then it's also good if you just have one example of RH in parallel, and then you can have it for running in the future. And I think after that, we will move to this side, and it will be very, very, very smooth transition, because I will say, okay, let's set the atom calcium and put these values there. And you will say, okay, now I understand, because we already did that for RH, and I understand now why we are doing the same for Desire. Or I said, okay, put these values on the Parkland or the broadening, so the broadening parameters for collision with hydrogen, put those values, and then you will know which file you need to look, and then which column is the one you need to modify. So this is just a suggestion. I think it makes sense, and you will learn 3 codes for the price of 1. That is also good. And as I said, I think, at least in my case, I still use SER for given things, RH for given things, and then Desire for other things. I feel that I will be doing this still for a long time. Okay, so just then let me finish. Yes, so please feel free to ask anything. I think there are no wrong questions, and in fact, maybe you have questions that I cannot answer. So don't feel bad if you think that the question is wrong or weird, because maybe I cannot answer. So then I will be the one that feels bad. This is just an idea, but I just want to mention it, that I think that there are so many people here that I would like to take the opportunity that at some point I will contact people to maybe give you a master class. And what I'm thinking is that, for example, as I said, we cannot really make models, atom models, but we can ask someone to teach us how to do it, or at least to be here to listen to our demands for our necessities. Or for example, as I said, I can teach you how to compute the broadening parameters for collisions with hydrogen, but most of the times I contact Paul to verify that what I did is correct. So maybe I can check if Paul is available to explain us in a master class of one day how to do it. And I think it's going to be much better for you. So idea is that just keep that in mind. I think we are so many that is a great opportunity to bother some people to come one day and reach a lot of researchers in one goal. So I have this in mind. So I think it's good, because then you don't need to listen only to me, and I know that it could be boring, and just keep it in mind. And then I think this is key. So in my case, I don't have clear idea of what I want to do. I have some ideas, as I mentioned, but I'm really open. I don't want to be strict on what we should do. If you have some requests, we just evaluate them, and then we put them inside, and we can go for it. So feel free to just tell me, I prefer to do things in a different way, and then we can discuss it together, and then we can reach an agreement. Okay, yeah, I think that's all. Okay, so I hope you enjoyed, and I know that it was a lot of, maybe I will stop sharing. Okay, so for now I will stop sharing, and then if you need that I go back, I will put the presentation. So please tell me what you think. You can raise your hand and just say something. I think the only question that I would really like to discuss is if we go through the option that I propose, or if you said, no, I want to just focus on this side. We can evaluate it. And the idea is that if you want to transform simulations and all the things that I show, you probably need SER and RH. So I think it's a win-win, but it depends on you.
Okay.
I have a comment.
Yes. Okay. Thank you. Yes.
Yes, I think that logically to go step by step through this SIR and RH and then finally get to desires is good. Makes a lot of sense, especially for people that are not very familiar yet. Mm-hmm. And so the only problem that we should consider is software. Installing software and getting it to run, it's always the biggest problem, especially in these remote settings, right?
Yes.
Where you're not there, but you just didn't put a comma there or something like that, right? The stupid thing that happens. Mm-hmm. And so since I do not know how these different codes run, this is a consideration that you should keep in mind, and that it might slow down your plan. That is what I wanted to say.
Yes. I think my goal is, so for example, if we go to this option, what I will do is probably tomorrow just send you the package of SER, and then the manual, and then ask people to run it. And the idea is that I will be available all the week. So if someone says, I'm trying to compile, but it doesn't work, so then I will try to help them. And I think also Basilio will help with that. So my idea is that try to ask people to install things 1 week in advance. So then when we reach the point where we are going to start, for example, with SER, I hope almost everyone is ready. Okay. But yes, I think for SER it's okay. But I know for design we're already having some OS compiling problems. So we know it's going to be funny. Okay. But
we are uploading everything to a GitHub page in order to I think it's easier for people to download all from
yes.
GitHub.
Yes, I think RH, the newest version is there, but I was not sure about SER. So you also have?
No, I have the
yes.
2007.
yes. But so I will send them. yes.
I have a load desire, but it's just in a private.
Yes. Okay. So
GitHub, but we can make it public.
Yes. But yes, I think it's something that for that we will be available. So just you can try it, and if you said, I'm just putting the sentence that the manual says, but it doesn't work, so then we will try. But yeah, basically I think it will be more delicate with Python. When we start the parallel wrap, then there you have to download the specific libraries. But I think Ricardo I will ask him to give just a course, or maybe we can record it. I don't know how to do it, but he will just try to tell you which libraries you need to download. But I know this is going to be dependent on which computer you use, if you have rights to install libraries, something like that. But I hope it will work. Okay, so
it's probably useful to start earlier with that rather than later. Point people to where they can get the code and let them get their hands dirty installing it. And by the time we get to the and maybe if you get a lot of questions, we can and I can certainly help with that on the RH side, for instance. But compile like FAQ where people that questions that regularly come up, so that you don't spend the time replying to individual emails all the time. But so over time, that will be a good resource. But I think in general, SIR and RH are fairly easy to install. They don't require a lot of libraries. So.
Yes, but yeah, let's do it this way. So let's try to, in parallel, try to make everyone installing the code, and then we can try to follow the class with your code compiling in your computer. Okay, yes. So there are two hands. So before the hands, just let me read the comments. Okay. Okay, Rebecca says yes, good. Nancy also okay, and then Don also okay. Okay, good, thank you. Ryan, I think you were the first one.
Hello, Carlos, and hello, everyone. I just wanted to make a small comment that I think you're right that you probably have a spectrum of people with different levels of experience with RH and SIR. And it might be worth sooner rather than later just briefly surveying people to get a numerical sense of how many people have used the codes and so on, and then also to monitor that in terms of how people are finding it each week. Mm-hmm. And then that'll help you decide, you know, you might find that SIR is really easy compared to how people are finding RH. And also I wanted to make a small comment about installing the codes. It might be worth having a session where you try to install all three at the beginning, and then the people that are more experienced can go and play with Desire in the meantime while you're running the earlier workshops.
Yes. Yes. Yes, for me it's fine. In fact, I forgot to say, so the idea is that I will share probably tomorrow the distribution of SIR, but next week I will send you the distribution of Desire and just a sentence of how to compile it. So the idea is that if someone wants to already work on it because they have more knowledge, we are already open it. So it will be fine. But I still strongly recommend to wait a bit because there are some new things and I think it's better to follow the flow, but we are not going to force anyone to do it. So we will send next week the Desire version as well. So you can have it and you can try install it in the computer that you plan to use.
Thank you.
Okay. Yeah. Okay. Sergio, I think. Yeah.
Yeah. Hi.
Hello.
Thank you for everything, Carlos. It was really nice, and I think taking also the option 2 will be the best. Even if I know how to use it, I think it is not hurting me to refresh many things that for sure I forgot how to use some of them. So it is the best. The other thing is that you said that we are going to use SIR. I'm only used to use the normal SIR, not the parallel version. I know that, for example, with Christoph, he was doing things to me this week with the parallel version. I guess that it is a kind of different, or you only need this Python stuff, as you said. So you need only to compile the C plus.
Yes.
Plus a wrapper.
Yes. The idea is that the wrapper is external element that takes the SIR computation that usually you have to do single thread, and it will divide it in different threads. So if you have multiple profiles, it will divide it the same initial configuration plus those multiple profiles in multiple CPUs. So the idea is that you learn first how to use SIR, and then the Python wrap will be just a script where you give general instructions, and internally is using all the files that you need for SIR. So it will be just an extra step. But the idea is that I think most of the people that have already used SER in the past, they don't know how to use it in parallel. So I think it will be also useful for people that still want to use SER. But it's something that I like the idea of Ricardo, because we are not changing at any moment, neither SER or RH. It's just an external call that will take what you're doing and share it. So if
it works in a higher level of circles, it just works in a higher level, I would say, as the standard source code for SER, Desire, and even RH. And all the packages they are, except one for the RH parallel wrapper, they are standard packages. So you can install them easily by the PIP procedure, or if you have an Conda or mini Conda, it's straightforward to install. Okay, we will prepare like a small routine to do this also.
What I use it is like in Hazel, Andres, it is normally putting all the Python stuff that you need in an environment, and then I'm always...
it will work perfectly for in that case. So you can have a dedicated environment just for these wrappers and just work on this, and you will not disturb your other environments. Or
yes.
Yes. So then it's I see it interesting, because those of you that already know how to use either SER or RH, we will help you to run it in parallel. So then it will be a big, I think, improvement. And those of you don't know too much about the codes, then it will be good, because you will learn everything. So, but yes, I know that the Python installation, it will be more delicate. So I think it's good if we start trying it. So I will talk with Ricardo to try to make something, maybe a video or something where we explain the steps, and you can start trying, at least for the SER version, that we will run it soon if everything goes well. Okay.
There is a question, Carlos. Basilio replied already.
Okay. Basilio replied. Okay.
Yes, on the chat.
Okay. Yes. So what was the question? Just let me know.
Was Ryan asking, does SER Python wrapper have the functionality to repeat inversions for a given pixel and keep the minimum chi-square output?
Yes. Well, in fact, it's implemented in the design wrap, and it's going to be implemented very soon in the SER.
It's already on the SER wrap. Yes.
The idea is that, well, I think this is getting technical, but just to let you know, so sometimes you run an inversion starting from 1 atmosphere. That's okay. But there are some chances that you could have better results. I will explain this later, but you could have better results if you have different atmospheres, that they are different. So for example, the velocity is opposite, the magnetic field inclination is opposite, or has a different sign, or the magnetic field has a different value. So then the parallel wrap will be able to, if you give like 3 atmospheres, the code will run, and it will invert with the 3 atmospheres, and it will take the best result of them. So then you are improving your chances to go to a global minimum instead of a local minimum. And the idea is that we are also making it a bit more clever, in the sense that we are going to say, okay, imagine that you give 10 initializations. So then this will mean 10 inversions. So it means that one computation will be 10 times much more slower. So 10 times slower than the normal one. So we are going to give the option to say, okay, that's fine, but also I'm happy with this threshold. So if you run the first time and the threshold is reached in the first iteration with the first atmosphere, then you don't need to do it 10 times. If it's not reached, then it will go increasing until you reach. So the idea is that we are trying to make it a bit clever, and you will see when you start using it that it will be not only faster because you can share between CPUs, but also because we are adding some things that will help speeding up the process itself. So yes, I think you will like it, even if it's only for the SER part. That is, it doesn't look like so modern compared to this side, but it's helping in a lot of things. So you will see that it's very helpful to install it. Okay, I think, yeah, Michalis, I think you want to say something.
Yes, well, first of all, I want to thank you and your colleagues at NSO Granada and Coimbra for putting this out. I think it's going to be a massive undertaking because many people are going to respond and want to use the codes.
Yes.
So the first thing I want to say is, don't hesitate to reach out to the more experienced people who are attending this session for help. Because, I think Jana kind of mentioned it, that those trivial comments from the non-expert users, which might be the more frustrating ones and might be the more impatient ones. So, I think you should perhaps reach out for help from some of the people who have experience with SER and RH, and that are not the developers of Desire. And the second thing is, I think NSO have this system with the Jira tickets where they log any errors. So I wonder whether that would be available to users, and whether that will be a useful way for people to put any comments and get any answers if there is a resolution to those comments.
Maybe Jana can say something, because I'm not sure about
we can look into that. Sure, that's I'm guessing that is mostly really DKIST related, and this is somewhat DKIST. Yeah, I mean, I will have to look into that, how that works.
Okay.
But that's a good suggestion. Thanks.
Okay, thanks, Michalis. And yes, I think I will try to keep up, but I'm afraid that maybe it will be better to ask for help. So I will do that. So thank you. Okay.
I was going to say that if you want to do the Jira ticket through a different platform, you can do something very similar on GitHub too.
Okay.
So you don't need to go through Jira.
I would second the suggestion from Rebecca about using GitHub. If you just have a repo for the course and people ask questions and follow, they get notified and people can help each other. So that would take a little bit of a load of you, Carlos. Yes. And also it's all recorded so that people can see how things are resolved later on, a few months later.
Okay.
Yeah.
Okay. Okay, great. Okay, so then I will look into that, and maybe I can ask Rebecca for help.
You can ask also Andres in house. So he's using GitHub, and he also using this kind of this GitHub to that you can tell him the errors and everything, and then he can fix it already from.
Okay. 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 Thank you. Yeah, definitely we will try. Let's see if Basilio can upload SER to GitHub.
There is a version of SER on GitHub that Luis uploaded a while ago.
Yeah, we have a GitHub that Ricky made. I asked him to put RH on GitHub for me. So Basilio, let's connect outside for that to see how we can best use that and leverage that.
Okay. Yeah, because Ricardo, in your case, it's GitLab, look what you are using, right?
Yes, the wrapper is on GitLab, but it's similar. So, and I can also create the GitHub account just for that.
Okay.
If you work with one, you work with the other. So the infrastructure is the same.
Okay, so then we will try that. So we can have maybe in separate threads, SER, RH, and the parallel wraps. So then we can separate the comments from each module.
Yes.
Okay. So, okay. Oh, good. So Rebecca put a link. Carlos, okay.
And I think there's another one by Luis. I know that,
Okay.
Carlos.
Yeah, okay.
Are they all slightly different versions?
Yes.
Well, that's the point.
Yes. I will try to convince Basilio to make
So we have to we have to make a Basilio approved one. That is the official one.
Yes. No, but the truth is that we need to use Basilio's one, so the newest one, because the good thing is that Basilio was making improvements when making this site to adapt the SER module to RH, and those improvements were also included in the SER version. So everything new in the, let's call it third part of design, it's also included in the standalone SER version. So the new version is, I think it's more capable. I will cover those things. Okay. Oh, Basilio has one. Yeah, but this is all one. I think Basilio.
Yes, I need to
yeah, this is
update.
2017. Yeah.
I
No,
need
no.
to update that.
It changed. But I promise that I will send you the newest one over the weekend, so you can at least have it locally, and then we will put it there. Okay.
Okay.
So do you like this strategy? So meeting regularly, discuss things, and go through all the things that I show you today. So do you like this idea? It's okay for you?
I think certainly with the option of people when they can't attend or they want to and just view the recording,
yes.
That's a very good option. And then it's good to go slow, because then people can say, well, I know this, I don't have to attend, and they can just quickly scan the video for something new that they were not aware of. So yes. I think it's a very good way. And I think looking at the comments, it looks like most people really prefer your option 2.
Okay.
So that's good. And as long as people are willing to share, that's great. Their recipes and methods. And
yes.
Yeah.
Okay. Okay. So
on that note, apologies that I only just showed up now. I accidentally fell back to sleep and missed the whole main thing, but was it decided what time this will be at going forward?
Yeah, not yet. So I will send a link to a doodle poll, hopefully tonight or tomorrow morning, and I will propose probably 2 or 3 times, and I think basically Thursday or Friday. So the idea is that you will fill it with your preference, and then we will pick the best option. Okay, but the idea is that we are going to record all the meetings. So if sometimes you cannot attend, it's fine. You will be able to watch what we said later on.
Awesome.
Okay, good. Okay, okay. There's a question. Yeah.
Hi, Carlos.
Hello.
Thank you very much for organizing this. I think it will be very useful for the community. So my question is maybe too technical and maybe too early to ask, but can you tell me please how far you can go towards the limb? So is the code works for low heliocentric angles?
Okay, I will answer, and then Basilio and Han will probably say if I'm correct. The idea is that the code works on the line of sight. So where you are, in principle, it will assume some line of sight, and it will give you atmospheric parameters based on that. So in principle, I don't see any problem on working on disk, on off limb. The only thing is that after that, you should think how you transform that line of sight atmospheric parameters to local ones. So, but I don't see a limitation itself to not run the code if you have an observation on the limb. But maybe Basilio or Han.
Except you need to keep inside the disk, because if you are outside of the disk, you are then the boundary condition in the integration of the is not good enough, because you are supposing that you are getting an optical depth large enough to suppose that you are setting the boundary condition for the radiation. If you are in a optically thin layer, the boundary condition need to be recalculated. We can do that if you like to invert observation outside of the disk then we will need to change the boundary condition for the integration, but there isn't any other problem. But in the present version, yeah.
Typically, with plane parallel solutions, you can't go much below 0.1, because then the path length in a plane parallel atmosphere become different from the path lengths in the spherical geometry. So RH has has a spherical version. So maybe for off-limb, we could leverage that. I'm not sure if we could combine it that way. That would be a whole different project. But typically, for plain parallel solutions, which this at the moment is, I would not go below 0.1.
Okay.
Just because of the path lengths.
So in your case, so you were thinking about off-limb, so like prominences and coronal rain.
Yes, piculs and off-limb structures.
Okay.
But also your papers about flare, those atmospheres and inverting those profiles of your papers, they should be really difficult to in the standard mode, no, of desired. I'm thinking about that. I'm assuming that your question is about more about your papers about this flare, limb flare, and going to there is quite difficult, no? In the classic.
Yes, well, for that flare, for that flare ribbon, we used radian simulation, but radian is similar to what Han mentioned. You can't go really off limb with radian. You should be inside the disk center. It should be on the disk. So yeah. I don't think we have, well, the spherical RH is the option, as Han mentioned, but it would be very useful if this type of codes also can synthesize off-limb emissions or invert. Yeah.
Okay. But don't say it now, because if not, Basilio this afternoon will start changing it, and I don't want that. No, yes. So I think it's a good point. I will take note, and I think if RH it's able to do it, I think it would be possible to also implement it on the side. But I think it's going to take a bit of time, because probably now we need to really check that it's working as intended with all the cases that we already have. But let's keep it in mind. I will put it as a note, and we will discuss it together inside the design team, and let's see what would we need to do, and if it's possible to do it in short term.
Thank you.
Okay, I think Ryan has another question. Yep.
Yeah. I was just wondering, how long do you figure it will be that be able to consistently make use of desire before it gets supplanted by convolutional neural networks?
I'm not sure about the question. So you believe that neural networks will work better than desired at some point? Is this your question?
Well, I'm just wondering because I know my group here at NSO, Kevin and Yvonne Han, we've talked about some of the CNN papers in the past, and looking at just how absurdly fast they are. So I'm just trying to suss out, like, if desire is X times faster than standard non-LTE inversion codes like STIC, and then convolutional neural networks might be another factor of Y times faster than desire. I'm just trying to figure out, like, where the different regimes of usefulness and effectiveness would be.
So I think, and this is, I'm not so sure if what I'm going to say is correct, but my impression is that there's some time to really, so you can teach the neural network to infer things, but I think until this point, it's difficult to teach it to keep it consistent physically. So sometimes you can obtain results that they look okay, but internally maybe the temperature, the electron density, or other atmospheric parameters, they are not so consistent. So I'm not so sure if you would be able to do that and when. And the idea is that with a stick or with Desire, you are solving the rate transfer equation, and everything, it could be wrong or correct, but in principle is consistent with the equations that you have. So I'm not so sure if speed is only the question here. So I think probably neural network, they will catch up, but I think the main problem is that I think it's difficult to teach it to be consistent as we have with RH or with Desire codes. But maybe people working on that can tell you more. But if you ask me, I feel that we are not going to be there in a few years, because I think it's.
Can I add something, Carlos?
Yes, yes.
So we have this other project that is also related with the convolutional neural networks. Actually, the paper was published on arXiv today or yesterday. And there we show some results that we obtained with the CNNs, trying to estimate some, basically mimicking inversions. And sometimes it works perfectly fine, but sometimes it fails. So we are still a little bit on the, not there yet. So our idea is to use the CNNs to initialize the inversions, and then we can speed up the process. This is already starting to be done for us a long time ago. So instead of using many cycles and many nodes, we use the neural network to initialize our initial atmosphere, sorry for the redundancy, and then we can reduce the computational time for quite a lot of time, in a factor of 6 or sometimes 10, depending on the non-ALT inversions that you are running. For example, if you need to run, back to the question before, like 3 or 4 different atmospheres, if you want to have a very good chi-square, with this CNN initialization, you can reduce this time a lot. But you need to have first proper inversions to train the neural network in a very consistent way, and yeah, that's the limitation. So I think we are still not there.
Okay,
Yeah.
I think
Also,
Rebecca.
Okay, I think that CNN are an easy way to solve problem, but Desire instead is a complicated way to complicate your life. And I think this is interesting because there is a way to introduce a lot of physics. I don't know, partial redistribution, illumination from outside, anything. You can, as you know the code, you can include different ingredients in order to make
Yes.
a more difficult life. I think this is interesting. It's just a game.
Yes. I think, Rebecca, you wanted to say something.
It doesn't matter, it was related. I mean, we're training neural networks on synthetic data from radiation hydrodynamic models. And I think one of the big limitations we have right now is the radiation hydrodynamic models do not produce spectra that are like the observation. So you can do the exercise, but you can't quite yet apply it to observations. So that's another limitation of that.
Yes.
And also the first code using neural networks, no, it wasn't by Hector Socas Navarro in early 2000, and we still use classic hardcore solving the rate transfer equations for more than 20 years. So. And you can also see the experience Hannah, Vasily, as soon as you code your question, they were like,
yes.
I don't think neural networks will ever completely replace. They will still be needed to verify that the neural network codes work right and to train them, honestly. So I think it's a bit denigrating to say it that way, but neural networks is glorified statistics, right? It doesn't have any. And now there are ways also to include more physics. So I shouldn't be as denigrating as I am, but and this will evolve maybe. But really I think still real inversions and full radiative transfer teaches what is going on in the sun, and that is something that you cannot get from neural networks.
Yes. So essentially, I would say that I see it as a good complement. And basically, what Ricardo was saying, that you can have different initial atmospheres, and one of them could be the result from a convolutional neural network. But still, in my case, I think it will be more consistent to run at least one cycle of desire, because all the physics that you are solving, they are consistent inside the equations that you have there. So I see them collaborating, but not fighting against each other. This is my impression. Okay, that's another raise hand, Dato. Or this is from before?
Well, it was before, yes.
Okay, sorry. Okay, so, but yes, we can bring this topic now and we can have it as a future thing, is that Ricardo already is working on training neural networks and having that result ready for the Python wrap that will call desire to read it and then use it as an initial atmosphere. So we are also integrating that. So in principle, it's not that we are not going to use it, it's that we believe that it will be like a complementary thing, that it will be there in the future. Okay, Ryan, I think you have another comment. Yeah.
Yeah. So I was just wondering. So Sir had this option to use the response functions to automatically select the node placements. And I seem to recall a paper a few years ago examining the possibility of doing something similar for non-LTE inversions. Does Desire have anything like that, or do you believe that it's even worth pursuing?
Yes.
Or is the automatic node selection sort of an ad hoc janky hack?
One second. So I think before going, I think the questions are very interesting, but maybe we can leave them for the time we are with the side. So I will let Basilio to answer that one, but I think these technical questions, we will cover them. So if you can just write them down, and then when we are ready with desire, for people will already know what you mean by automatic selection of nodes, because we have already covered SER. So by that time, we will revise that, but just let Basilio answer this one. And then we will leave the other technical ones for the future, because I think most of the people are not really following what you are saying.
Okay, but the answer is yes, because Desire is a mix of SER and RH, and then it takes both capabilities of both codes. Then anything that RH can do can be solved, but in the 1D case, of course, and everything that SER can do can be done by Desire. Then you can select automatic selection of nodes, 2 atmospheres, and many other possibilities that you can work with SER. But we have not checked that. Okay, we have not, but I want to suppose that it will work, but we have never played with that.
Yeah,
but
we will check it.
In principle, we will check that. Okay, I think in principle it runs.
Yes. Okay, so I think it's better if you just if you have general questions, we can go through them, and if not, we can just finally decide that everyone agrees with what I propose, and then let me discuss tomorrow that I will meet the design team how we do the installation of the different packages to try to make it as simple as possible. And the idea is that next week I will just start with SER, and I will go one by one of the configuration files, try to explain you more or less everything that is there, and teaching you how to run it. I didn't say it before, but my idea is to make it very functional. So I will try to just tell you how to make it run. But if you feel that this is not enough, then at some point I will ask Han and Basilio to give a proper introduction of the basics and the physics of the codes. But the idea is that for now, I just want you to allow you to play with the code, to learn how to run things, what different parameters mean, but I will not really enter on defining response functions with equations or other things, because I believe it's probably a bit funnier to just work a bit with the code. And then if you feel that you need more, then we are able to go there. But for now, I think it's better to not really put you a lot of equations in front and confuse you more than than you need. Okay, so so then you will receive a mail. As I said, those of you that you have not tell me that you want to participate, or you didn't receive a mail from me inviting you, please send me an email so I can add you to the list of participants, and then you will be receiving all the correspondence from now. And then I will send a doodle poll today, probably, so then you can fill it, and I will close it hopefully Sunday or Monday. And then we will meet next week, and we will start step by step with SER. Hopefully everyone will have SER installed in their computers. Okay. Okay, so.
Okay, great.
Okay,
thank you.
So thank you very much. As I said before, I think it's really nice to have all of you wanting to learn from us, because it's really encouraging, and I really feel good knowing that you are interested in the code. So thank you.
Travis. Yeah, thanks everyone.
Bye.
Bye.
See you.
Bye.
Bye. Bye. Bye. Han, Basilio, maybe you can stay. Maybe once. Yeah.
Chat.
Yeah, you can stay 1 second. Maybe I can stop recording.